Okay, welcome everybody. This is the week seven webinar for the online statistics class. So we are past the halfway point, just a little bit. And let me tell you the plan. So what we're going to be doing is, as always, I'll answer any questions you have, and that could be the beginning or anywhere throughout. I'm always looking at the chat box, and feel free to ask any questions. And then after that, we're going to get into what's called the null and alternative hypotheses. This is something that you learned, kind of what we're doing today. You actually learned this in like ninth grade or 10th grade when you learned the scientific method. You've probably heard of that before. You probably learned it in high school. But now we're going to be looking at the statistics part of the scientific method. And, it's a step-by-step the scientific method has, but we're actually going to do it instead of just talk about it. So the first step in the scientific method will be decide on the null and alternative hypotheses. The next step will be type 1 and type 2 errors. I don't expect these to make any sense to you yet, but they will hopefully by the end of this webinar. Then after that, we'll look at level of significance and how you make that decision. Then we'll look at the p-value. Then we'll talk about how do you state the conclusion. Then we'll interpret the p-value. Then we'll interpret the level of significance. And then finally, project 1 is over. I graded them last week, and I want to let you know, project 2 is the next project to look at. We have 2 projects, so kind of cut the class in half is the idea. And so we're going to just talk about planning project 2. Next week, we'll talk about the details of project 2, because next week is when we'll go over chapter 10, and that's what project 2 focuses on. But we'll get some of the ideas in chapter 9. So that is the plan. And just to let you know, my background is where I was, where I did a 20-mile hike today, and that's where I ended up. It was Star Lake, which is a frozen lake right now. So it's totally ice and snow. So just that was my thing today. So are there any questions about anything? Any questions? Again, I'm always happy to answer questions. And if you come up with them, you can drop them in the chat box too anytime. Okay, if there aren't any questions, let's move on. We're going to be doing hypothesis testing today, which is pretty much, that's what we're going to be doing for the rest of the entire course. So pay attention today, because this stuff is needed for everything we're going to be doing for the rest of the class, rest of this whole course for the next, 5 weeks. So one of the interesting things is I always do an example hypothesis test, but I also like to do what's, the big headline of the news, because I like to convince you all that statistics is used everywhere. And it turned out that the number one example I've been using for the last bunch of years was number one in the news today. Anyone know number one in the news today? Biggest thing in the news on CNN, at least. Is their top story? Okay, so here it is. CNN's headline was the FDA may limit future COVID-19 shots to older people and those at risk of serious infection. Okay. And by the way, I'm pretty old, but I'm not old enough. So if this really happens, then I can't get another COVID shot, and I've gotten my COVID shots. And I'm going to explain today why I got the COVID shot. I'm not a doctor, so I have no idea what what it means to be at risk. Sorry about that. So cancer might be one of them, but I really don't know. I know obesity is one, and I'm not obese, by the way. But and I don't think I have anything that is a serious risk. But still, I get my shots. So I want to talk about, how it is that these companies, Moderna and Pfizer, those are the 2 main companies. I guess there's J&J too, that, got their initial COVID shot accepted. What did they do to get the acceptance from the FDA to be able to originally to get the shot? okay, to give the shot out to everybody. And just let you know that when they did open it up, I read the article, I read their research, and I looked at their statistics because to me, I care. I want to make sure they're doing things right. And we'll see whether they're doing things right because I actually will give you the statistics on the original testing to see if the COVID shot works or not. That makes sense. So the first thing you have to do, kind of imagine you being the statistician for Pfizer for Moderna, and you have to show that the shot works. So the first thing you have to do is you have to set up what are called the hypotheses, which are there's two hypotheses. One is called the null hypothesis, and that is the shot does nothing for you. Doesn't work, doesn't do anything, doesn't help at all. And the other is the alternative hypothesis, and that's the shot works. Okay, and what they did is that their plan was they give a whole bunch of people shots. Okay. And actually what they did is they did a test and they wanted to see if those who got the vaccination shot were less likely to get COVID. Does that make sense? So the null hypothesis at the time, this was the original data, 4% of the population within the months that they were looking at got COVID. So that's forget shots. That's just how it was then when it was originally happening. 4%, 400 people were getting COVID. Okay. So what they did is they said the null hypothesis. The null hypothesis was that P here stands for the proportion. P for proportion, and it's a population proportion. We've seen that letter before. And that after getting the shot, you still have a 4% chance of getting COVID. Because if you still have a 4% chance of getting COVID after getting the shot, and that's what everyone else not getting a shot has, then the shot's worthless. Is that clear? Okay, just want to let you know the notation we use is we use the letter H. Okay, H is the first letter of the word hypothesis. So that's why we use H. Okay, and that's not just me, that's everyone in at least that does English. I think I've seen it in Japan too, and they use H also, even though they use different letters, but they use our letter. And then down here, in America, we think of it as a zero, but actually the British got to it before the Americans did. And anyone know what you call the number zero if you're British? It's not a math question? Not. Yeah. Actually, it's N-A-U-G-H-T. Yeah. So it's H naught. So when you hear me say H naught, naught does not mean no. It means the initial hypothesis. And then you put a colon. I want to let you know, do not put an equal right there. A lot of people make that mistake. It's a colon. And colons are easy because that's, shift right next to the L and that'll give you the colon. So it's easy on the computer to get a colon. And then we write P equals 0.4. Okay. Whereas the alternative hypothesis is what these companies, Pfizer and Moderna, were trying to show. They were trying to show that the vaccination actually worked. And if it worked, it means that your probability of getting COVID was reduced when you got your vaccination shot. Does that make sense? So we write H1. And I want to let you know, depending on the book, some people use 1, some people use A. I tend to use 1 because I don't know, 1 seems to go well after 0 and then 1. But if you want to use A, that's your choice, and you might see A sometimes. So, but I'm going to use H1 and then colon, and then P for the population proportion of those who get COVID after vaccination. is less than 4% or less than 0.04. Any questions, and this is called the alternative hypothesis, the second one. Any questions on what it means to state the null hypothesis and the alternative hypothesis? Okay. And just to note, you can type these. Okay. So you can type these. If you don't want to use subscripts, you can just use that like shift underscore thing and then type in a 1. That's fine too. The rest is really easy to type. Any questions at all on the null hypothesis and the alternative hypothesis for this example? All right, so now we want to look at what we call the ramifications of a type 1 and type 2 error. Who knows? This is not a math question. This is an English question. Who knows what the word ramifications mean? I know a lot of people have trouble with that. They don't know that English word. You know what ramifications are? Yeah, the consequences. I like to say the easy way of saying it, the bad stuff that happens. Okay? So what are the bad things that happen in the errors that could happen? So let's talk about what these errors are. The first is called a type 1 error. So a type 1 error means that you reject the null hypothesis when the null hypothesis was true. Okay, so that means that Pfizer and Moderna said, hey, we looked at our data and yeah, we got good evidence, statistical evidence. We're going to call it statistically significant evidence that the vaccination does reduce your chance of getting COVID. But the null hypothesis is true means that the vaccination doesn't help at all. Okay? If that happens, is that bad or is it good? What are the ramifications if that happens? Any thoughts? Yeah, so there's 2 ramifications. It depends on how you look at it. One is money. Okay. You spend a lot of money vaccinating all these people. Okay. And it didn't help at all. Okay. Another one actually is a biggie, and that is, hey, when I got vaccinated, I'm not sure if you all got vaccinated too, but hopefully you did. When I got vaccinated, right after, a month after when it was, when it sunk in, they call it, I went and saw my family because then I felt pretty safe and I wasn't going to kill my family, or my friends. So on the other hand, if the vaccination didn't work, then yeah, I might have gotten COVID from them, or maybe I got COVID and they get it from me. Do you see? So that there's all kinds of the ramifications on a type 1 error. Okay. So again, in terms of what I've written, the vaccination gets approved. It doesn't work. People go through the vaccination process. And I don't know about you, but did you get tired after you got your vaccination? I got so tired the next day. I actually gave a test the next day last time, and I fell asleep during the test. It was a little weird. Okay. And also could have been overconfident because then I feel like I'm not going to get COVID or give other people COVID. Okay. And then maybe I'll get COVID. Okay. When I didn't think I was going to get it. So that's a pretty bad ramification, right? Okay. Yeah. I actually did get COVID after getting my 3rd shot. But again, I was sick for a week and then I got better. If I had not gotten shot, I might have died. So look at it that way. And, for all of you who got sick or whatever, lost pounds, sweat or whatever, had you not gotten the shot, maybe you would have died. So it could have been worse. Okay, now here's a type 2 error. Okay. By the way, often in medicine, they call a type 1 error a false positive. A type 2 error is there's not enough evidence to reject the null hypothesis. So we call it failed to reject the null hypothesis when the null hypothesis was false. This is a little bit confusing because it turns out you never accept the null hypothesis. That's really important to note. All you do is say, we don't know if the null hypothesis is true or false. So we just don't have evidence. And if you don't have evidence, then the FDA is not going to approve the drug. Okay? Not going to approve the vaccination. So what are the ramifications in that case? They're not going to approve it when it actually worked. What are the ramifications? Ideas? Yeah, no one gets vaccinated. And what happens to all these people? Or a lot of these, not all the people, but yeah, a lot of people end up dying when they didn't need to because they could have gotten vaccinated. Okay, so the vaccination does not get approved. It really does work and nobody gets vaccinated, and 1 million more people still die of COVID. Okay, that's a bad ramification. Any questions on the type 1 and type 2 errors? Okay, these are examples. Okay, there's lots and lots of examples and we'll do some others too. So there's just one example because the definition is a little, kind of abstract. It's easier to do it by example. Okay, so the next step, by the way, this is a step-by-step process. Okay, so step 1 is you decide on your null hypothesis and alternative hypothesis. Step 2 is you determine the ramifications of a type 1 and type 2 error. And step 3 is decide on what's called the level of significance. Okay, so here's the definition of level of significance. The level of significance, okay, is the probability of a type 1 error. Okay. So the standard level of significance is 5%. It doesn't mean you have to always use 5%, but 5% is standard. Okay. So that means you have a 5% chance of a type 1 error if you use the standard level of significance. Okay. Now for us, we're going to always use 0.01, 0.05, or 0.10. Okay. So it turns out if you want a smaller probability of a type 1 error and you don't change your surveying at all, then you're going to then you end up increasing the probability of a type 2 error and vice versa. If you want if you don't care that much for a type 1 error, so you're okay with a high probability, like a 10% chance or 0.1 of a type 1 error, then you have a smaller chance of a type 2 error. Any questions on that idea? Okay, so it's a give and take thing. You increase one, the other goes down. You decrease one, the other goes up. Okay, so the type 2 error possibly kills hundreds of thousands of people that could have been prevented. I think that's worse. Maybe you don't, but I think that's worse. If the type 2 error is worse, then we should probably use a level of significance of 0.10. I like to call it 0.10 instead of 0.1 because then it looks like 10%. But you can call it 0.1 if you want. I want to let you know, do you know what this letter is? It's a Greek letter. Do you know how to read it? Yeah, that's the Greek letter alpha. It's the first letter of the Greek alphabet. When I was a kid, everyone knew alpha and beta, the first two, because that was the name of the most common supermarket, Alpha Beta. And now people don't know it as much because I don't think it even exists anymore. But the letter still exists. So we're going to use alpha as a standard letter for the level of significance. Any questions on why I chose 0.1. Okay, so again, that means that we're going to have a higher chance of a type 1 error and a lower chance of a type 2 error. Okay, so the next step. Next step turns out in the real world is the hardest step there is, and that is collect your data. Okay, so, in this case, you can't just give, 10 people shots. That's not a big enough sample size. Okay. They actually gave 40,000 shots because they really wanted to make sure that their data was good. Okay. That 40,000 was the sample size. Okay. And they actually did a randomized control study, which means that they got 40,000 volunteers and then they used a computer and they randomly selected, I don't know about half of them, but let's suppose half of them to get the real shot, and the other half got a placebo shot. So that everyone thought they got the shot. Otherwise, there could be other issues, placebo issues. So that's how they did it. And that's how they really did it. I read about all this stuff. So the next step is collect the data. In that case, if you get a sample size of 40,000, that's a lot of work. Okay. Just finding people is really hard, but even giving 40,000 shots is a lot of work. And then you got to, contact them in the next month or two, keep testing them for COVID to see if they're getting COVID. So that's actually, even though it doesn't look like the most work in terms of our class, but in the real world, that's the biggest job, is the collecting the data. Okay, the next step is to put the data into the computer and calculate the p-value. Okay, then you compare the p-value with the level of significance. The p-value, let me write if p-val is less than alpha, then you reject the null hypothesis and you accept the alternative hypothesis. Any questions on that idea? Any questions? Okay, so if p is greater than alpha, you fail to reject the null hypothesis. I want to let you know accepting the null hypothesis means, hey, I've got it. I know this is true. Failing to reject is a fancy way of saying, I now know nothing, which is not what you want. So let me show you a picture. So what you do next is you say, if the probability of getting COVID after getting the shot really is 0.04, and for the I think it's Pfizer, for their test, 1% instead of 4% got COVID after getting the shot. So what would the probability be that if it really is 4% and you gave 40,000 people the shot, or maybe 20,000 if it was a placebo test, then what would the probability be that 1% or fewer would get COVID if the shot really doesn't do anything? Does that make sense? And that probability is the p-value. And if you have a large enough sample size, then the central limit theorem says that this can be calculated using the normal distribution. Hopefully this gives you a reminder of something that we've already done. I did it to just give you a heads up on what was coming. And that was the discussion post, not last week, but the week before. Do you remember that's what you had to do? You had to compute the probability that if it was what they, kind of the general idea, and you did another test of that many people, what would the probability be of having it at least that or more that extreme or more extreme as what you got in your test? Okay, so this is actually exactly what you had to do in your discussion post assignment in week 5. I know it's been a couple weeks, but hopefully you remember that. Do you remember that? Okay. It turns out that the p-value they got was 0.004. That is much less than 0.1. Is that clear? So the area under this curve turned out to be 0.004. So here is a wording that we use to make our conclusion in this case. So first thing, if it's less than 0.01, we're going to use the word strong. If it's not less than 0.01, we don't use the word strong. So keep that in mind. So make sure you use it when you should. So there is strong, statistically significant evidence. Okay, I'm putting that in red. Maybe I'll boldface it too. So strong, statistically significant evidence to conclude that the population proportion of vaccinated people who get COVID is less than 0.04. If I yell it and I bold it and put it in red, what does that mean? Do you remember for this class? This is not the first time. It's important, and if you don't include these words, you lose points on the exams and the discussion post. Okay, so it is very important to make sure you have the right wording. Got it? And this is the standard wording. In fact, a lot of you on the confidence interval, when I told you you had to refer to the population, didn't. And if you don't refer to the population, you lose points. Okay, so that's just a note. Any questions on this? Okay, so if there's strong statistically significant evidence to conclude the population proportion of vaccinated people who get COVID is less than 4%, what happened? We're talking, like 4.5 years ago. What happened? Because of that. This is history, but not that long ago. Some of you were kids. You remember? Okay, I don't see y'all jumping in. Okay, what happened is because they found strong statistically significant evidence to conclude the population proportion of vaccinated people who get COVID is less than the 4%, which is the percent of regular people who got COVID, the FDA approved the drug. Okay, and that is a requirement of the FDA, which is a federal drug, I don't think it's administration, might be associated. I think it's administration, FDA. Okay, so that's what you have to do to get a drug approved. Yeah, you have to make sure that they have done, that a hypothesis test was done, and they got statistically significant evidence to show that the procedure or the vaccination or whatever that medicine is worked. If they don't show that, it doesn't get approved. Any questions on how important this is and what this is all about? Any questions? Okay, so let's interpret the p-value now. Okay, so what does it mean to have a p-value in this case of 0.01 is what they had for their p-value was 0.004. Okay. All right, so here's what and again, the p-value is 0.004. Notice the 0.04 was the percentage of people who got COVID had they not gotten the vaccination. So sorry, this is real, so the numbers look similar, but they're not. Okay, so if the population proportion of all vaccinated people who get COVID is 0.04. So in other words, if the vaccination didn't work at all, which means that it doesn't help you one bit. So you still have a 4% chance of getting COVID even after you got vaccinated. If that was true, and if another study it turned out that I did research it a while back, I now remember, 25,000 people were vaccinated. Okay. And COVID tested during and at the end of the testing time. Then there would be a 0.4%, because that's the p-value was 0.004, which is 0.4%. So there'd be a 0.4% probability that fewer than 1% of them, 1% because that's how many in the trial got it, that fewer than 1% of them would get COVID. Any questions on interpreting the p-value? Any questions? I do want to let you know there's a lot of writing. Okay. So make sure you practice. Okay. A lot of the homework questions are multiple choice. So especially the written stuff, the stuff that is computer graded is all multiple choice. So what I recommend is don't even look at the choices originally. Write down what you think the answer is, then look at the choices. And that way you'll get used to writing down your answer. Any questions on that? Writing down can be typing too, because on the exams you have to type. Okay, for the last couple questions. Okay, now interpret the level of significance. Okay, turns out the level of significance starts exactly the same. So let me highlight up to here. And if you look at interpreting the level of significance, it's the same start. If the population proportion of all vaccinated people who get COVID is 0.04, and if another study of 25,000 were vaccinated and COVID tested during and at the end of testing time, then there would be, and now things change because our level of significance is 10%. And remember, the level of significance is the probability of a type 1 error, which means type 1 error means that if the null hypothesis is true, so what's highlighted in what I just highlighted was the null hypothesis being true. That means if the mean and the proportion really was 4%. Okay, then there'd be that probability, because that's the probability of a type 1 error, a 10% probability that a type 1 error says the null hypothesis is true, but you ended up saying there's statistically significant evidence that the alternative hypothesis is true. So we'd end up falsely concluding that fewer than 4% of all vaccinated people get COVID during these months. Any questions on this example? Okay, this is a real example. I consider this the most important example in the last 10 years at least of any hypothesis test. Maybe you may not agree, and that's okay, but I think this was a biggie, is making sure that the vaccination worked. Okay. By the way, it doesn't mean you can't get COVID, but it means that you have a smaller chance of getting COVID if you get vaccinated. Do you see how that works? You have smaller than the standard probability of people who don't get vaccinated. Those who do get vaccinated have a smaller probability than that. Any questions on interpreting the level of significance? Okay. Note that, this is all, and this is very important, that, this is all about COVID and testing and all that stuff. Don't just do what I'm about to show you, what I'm going to show you in a little bit. Just note that null hypothesis is what you're hoping to refute. The alternative is what you're hoping to find evidence that is true. Okay. And sometimes you actually, when you're saying hoping, it means that's what you're doing the test about. Sometimes you don't want it to be true because there's some tests where you want to test to see if, I don't know, people get sick all the time. You don't want people to get sick all the time, but you want to find out if it's true or not. Do you see that? So you're doing the test. Okay. And just to note another one, and that is that you never, ever, ever, ever say the null hypothesis is true based on your data. You can't do that. You can only say there's statistically significant evidence for the alternative hypothesis to be true. You fail to reject is not the same thing as saying accept. Okay, so now let's go to another example. Sound good? So this is something I did about a week and a half ago. And that is, there was something called Snapshot Day. Those in Tahoe, you might have heard of it. What we do is they get volunteers, and I'm one of the volunteers. Okay. And I went to a creek. If you know Tahoe, actually, this year I went to Meeks Bay. It was beautiful there. And one of the things we did is we looked at the pH of the water that flows into Lake Tahoe, kind of through Meeks Bay, on the creek that goes through. Okay. And I collected one data point, just let you know that. And there were four of us actually at Meeks Bay. But I think there were 80 volunteers. So there were pretty many data points, and they've been doing this for, I think it's 24 years, 25 years, something like that. And I've done it every time except one where they didn't have it unless you worked there because of COVID. But this is what we do. And again, it's just volunteer. You can do it too every year. It's in May. And the question is, does the average pH in streams that flow into Lake Tahoe differ from 7.0? I'm not sure if you've had chemistry, but the standard pH of water is 7. Okay. I'm not going to get into all the chemistry, but you might have heard of pH, hopefully. And it turns out that if the pH is very far, is not 7, if it's like, 4, then it's very acidic and it kills everything. And the same thing if it was 10, it's very what they call basic and it kills everything. So the idea, this is an environmental, kind of environmental testing to look at whether the environment is a problem in Tahoe. Does that make sense? And it's a problem if it differs from 7. Whereas on the last one, we wanted to make sure that people were less likely to get COVID. Here, either side is bad. Do you see that or different? All right, so the first step so the step-by-step process is always the same. The first step is you write down the null hypothesis and you write down the alternative hypothesis. So H naught. So now, if you've ever looked at pH, the pH, by the way, the pH we got, the pH that I got when I put the little pH meter into Meeks Bay water was 7.1. Okay, so notice that it's not a yes, no, it's a number. Whereas vaccination, you either get COVID or you don't get COVID. Does that make sense? So that was of proportions. The data is quantitative. So this is a test for mean, for a population mean, not for a population proportion. So H naught is mu equals 7.0, because the idea is, hey, if there's no issues, then the population mean pH of the streams that flow into Tahoe are 7. That's a good thing, by the way. Whereas H1, the alternative hypothesis, is the population mean pH of the streams that flow into Tahoe is not 7. So use not equal to. Okay. If you want, by the way, if you don't know how to type not equal sign in there like I do, you can write not equal, and I'll accept that on your exams and on your discussion posts, if that makes sense. It turns out in the project, if you end up having a not equal, then I want you to do it in symbols because then you can get lots of help. You have not basically unlimited time. So I'll help you, the tutors will help you, whatever, on how to do it. Okay, but for the exams where they're timed and stuff, if you write not with the equal sign, that I'll accept that. Sound fair? Any questions on this? Okay, step-by-step process. First step, you decide on the hypotheses. Second step, who remembers the second step? What's the next step after deciding what H naught and H1 are? Is this just like the last example? Do you remember? Level of significance is the third step. Good try, though. Data, that's the fourth step. The second step was decide on the ramifications of a type 1 and type 2 error. Do you remember that? Yeah, type error. Yeah, the bad stuff that could happen if the test kind of drew you the wrong way. Okay. And by the way, this is when you have a not equal to it, we call it a two-tailed test. And the reason we call it a two-tailed test, if you look at the normal curve, if it's far left or far right, then that means that H1 is going to be, you're going to have a statistically significant evidence for accepting the alternative hypothesis on either left or right. So that both tails will give you a reject the hypothesis, reject the null hypothesis. So that's why we call it a two-tailed test. That's the language. Okay, so type 1. Let's look at think about the type 1 issues. So that means we have statistically significant evidence to show the pH differs from 7 when it is 7. So in other words, the water is wonderful. There's no problems with the water flowing into Tahoe. But for some reason, our data showed evidence that the water is not good. Okay. If that happened, then the government will be able to fund a very expensive project to mitigate the pH issues in the creek. But it didn't need to be done because the creeks were fine. And the big ramification is it's a total waste of money because you're going to spend all this money to deal with pH issues, and you didn't need to, but you still spent the money. So that's an error. That's a ramification. Now let's look at the type 2 error. Type 2 error means that you didn't have evidence to support the claim that the pH differs from 7, but it really does differ from 7. So if you don't have evidence to show the pH differs from 7, the government's not going to give you any money to deal with the environmental problems. But guess what? There's an environmental problem. So no funding is going to happen. And we have this like either giant pH or really low pH, and the plant and animals are going to go extinct in Tahoe. We're going to have an environmental disaster. What do you think is worse, by the way? By the way, it could be either way. You decide. This has to do with your feelings. So I'll tell you what I think is worse, but that's not a stats thing. That's it. And by the way, on your exams and stuff, I'm going to ask you to explain why you choose the level of significance, and you have to talk about which is worse, based on which is worse. So which is worse, type 1 error or type 2 error? What do you think? Which one? 1 or 2? It's easy to type. Okay. Okay, at least those that typed it in, you're like me, you're an environmentalist. You care about the environment, and you think it's worth, spending money it would be bad if we wasted money, but it'd be even worse if we destroyed the environment. And by the way, these statistical tests are also done, just in case you don't live in Tahoe, they're done for things like climate change. Because if there's no climate change, there's no reason to spend money and have rules and anything. But if you do have climate change and you don't fix it, we have disasters. So it's kind of the same idea. And by the whole climate change thing was all statistically shown and very statistically significant. So same idea. So I think the type 2 error is worse. So the type 2 error is worse. Let's use 0.1 again. If type 1 is worse, use 0.01. If they're about the same, then use 0.05 in our class. And that's required. Okay. So now let's suppose and actually isn't suppose, let's suppose X bar was 6.4 and S, the standard deviation of the sample, was 3.5. So the sample mean was 6.4. The standard deviation of the sample was 3.5. And let's suppose we looked at 15 creeks. Okay. Just note that N is 15. 15 is less than 31. So we must assume the distribution of pH levels is normal, or you can't do any statistics. Okay. So now if you look over many years, then you'll have a bigger sample size. But in 1 year, 15 creeks is about what they do. That make sense? All right. So now we need to find the p-value. On the last one, I just gave it to you. How do you think we might find the p-value? What's your guess? Any ideas? It should be obvious. I don't see you jumping in. We're going to use a calculator. So let's go to the calculator. Tell me which calculator number we should use. Yeah, this is a hypothesis test for a mean with statistics. Okay. In terms of the question, it didn't have the data. It just has statistics. We have a mean, not a proportion. And here it is. So the first thing is sigma known or sigma unknown. Sigma unknown is almost always the case, but some other faculty wanted me to give choices. So sigma unknown is almost always going to happen because if you know sigma, you probably know x in mu, and then you don't need to do a hypothesis test because you know the population mean. But just let you know, sigma unknown is what we want. Then we have S, and S was 3.5. That's the sample standard deviation. Then we had X bar was 6.4, the sample mean. Then we had N, which was the sample size. That was 15. See this mu naught? That is the mu that's written in H naught. So if you go to H naught, then we have mu is 7.0. So our mu naught will be 7.0, which is the same as 7. Then it's either less than, greater than, or not equal to. Which is it in our case? Remember? I don't see jumping in. Let's look again. So the key is, what do you see? Yeah, not equal to. Okay, so not equal. So I'm going to click on the not equal to. Then I hit calculate. And there we go. It gives a bunch of things. It gives the test, what's called the test statistic. Okay, and that is T because we don't know the standard deviation. This is, you got to have that student's T test is the idea. Remember, student's T distribution, because that gives you that little extra issue because you don't know the population standard deviation. You can't use the normal distribution exactly. You use this kind of modified one, which is called T, and that is negative 0.66 or so. And then we have the P, our P value, 0.5175 or so. Okay, and here's the picture, by the way. Here's your 6.4. Here's the 7. And what I did is I shaded in what's called the rejection regions. So if you're in the rejection region, you reject the null hypothesis. If you're not in the rejection region, you fail to reject because our p-value, in other words, the proportion, the area to the left of this, and also if we go to the opposite side and we go to the right of that and add those up, that gives us the 0.5175. If you're way over here, it's a much smaller number and from both sides. So then you'll actually reject the null hypothesis. Okay, but here our p-value is 0.5175. Our test statistic is negative 0.6639. So negative 0.6639, and our p-value is 0.5175. Okay. Now, here our p-value is definitely big. It's bigger, so 0.52 is bigger than 0.1. Does that make sense? Okay, here's 6.4. That's what we got. How did I get the 7.6? Just want to make sure you understand this. Anyone know how that number came about? Because it's important that you understand it, because you might be asked to do it. Okay, the idea here is 7 is the null hypothesis number. 6.4 is 0.6 below 7. So remember, this is a distribution that has symmetry. So if we go 6.6 above, you get 7 plus 0.6, which is 7.6. So then it's a two-tailed test. So the right-hand side of that 7.6 and the left-hand side of the 6.4, the combined area is 0.5175. Any questions on that? Okay, so notice P is very large. Here's something that I like to say just because you might remember. If you go to a restaurant and they give you peas, okay, as your vegetable, do you expect them to be large or small if they're peas? Yeah, they're small. You want your peas to be small. If they give you peas in a restaurant and it's as big as an orange, you're like, oh no. You want little p's. Little p's mean you get to reject the null hypothesis. A big P means you fail to reject. Got it? That's one way to remember. Okay. So the P value is 0.52, which is greater than 0.1. So the conclusion is there's statistically insignificant evidence to support the claim that the population mean pH of water that flows into Tahoe differs from 7.0. Okay, there's a very fancy way of saying that we did the study and we don't know anything. We can't conclude anything we don't know. It does not say the population mean is less than 0.1. It doesn't say it's greater than 0.1. Population mean is greater than 7 or less than 7 or equal 7. We don't know anything. We just have a fancy way of saying we don't know anything. Any questions on that? All right. What does it mean to have a p-value of 0.5175? So what that means is that if the population mean pH in all creeks that flow into Lake Tahoe is 7.0, and if we measured another 15 creeks, then there would be a 52% chance that the sample mean for the new study would either be less than 6.4 or greater than 7.6. I do want to note that this first part is about population mean, and this last part is about the sample mean. And it is important that you identify, if you ever have the word mean, you better put that word, either sample or population, depending on what it represents. Okay, any questions on that? Okay, let's interpret the level of significance. So same idea. If the population mean pH in all creeks that flow into Lake Tahoe is 7, and if we measured another 15 creeks, then there'd be a 10% chance, that's what our level of significance was, that we would end up falsely concluding that the population mean pH of creeks that flow into Lake Tahoe differs from 7. Any questions on this interpretation of level significance? Very similar to the last idea, but notice that the words are all about creeks and pH and stuff. Where the last one was about vaccinations, getting COVID. Okay, but statistically, it's just kind of the same idea. Okay, and it's important to know whether you're talking about mean or proportion. So notice here, mean. Don't mix those up. You lose points if you refer to proportion when it's a mean or vice versa. Any questions at all on this example? Okay, ready for another example? Okay, this is all about examples. Okay, let's suppose that you want to see if women are not drinking the recommended 2.7 liters per day on average. Okay, I don't know if you know that, but you're supposed to drink 2.7 liters. Okay, and that's of good drinking, not not vodka, by the way. That's like if you're in Tahoe, our Tahoe tap water is like the best in the world. But it could be orange juice too. Okay. Any questions on the question? Okay, so the null hypothesis here, we want to see if women are not drinking the recommended 2.7. Okay, so again, what you're going to ask is, hey, are you drinking? How much water or how much liquid are you drinking every day? And if the population mean is 2.7, hey, then the average woman is drinking the right amount, you see? So that's H naught. On the other hand, if women are not drinking the recommended 2.7, then mu would be less than 2.7. Any questions on that? Okay, let's suppose we decided on a 0.1 level of significance. Okay, we only have so much time, so I'm just kind of going through that. You can talk about the type 1 and type 2 errors and come up with all that stuff if you want. And let's suppose that you looked at a bunch of women, and this is the data that they gave you. I'm going to copy this. So the first woman drank 2.4 liters, the second 2.8, the third 2.9, the next 2.2, et cetera, et cetera. Then we need the test statistic and the p-value. Let's go back to the calculator. What calculator number do we do? Yeah, this will be 15 because we're doing a hypothesis test. It's for a mean, it's a mu. And this time we have the data, not the statistics. So I'm going to click on that. And it says type in the data separated by commas. So the nice thing is copy and paste works really well. Otherwise, this would have taken a long time. All right. We don't know sigma, so leave it blank. And we want less than, because that was what H naught was, if you look over here. I mean, H1. H1 is mu is less than 2.7. And 2.7 was our mu naught. Any questions on that? And I click calculate, and there it is. And what I get is our X bar was 2.54. That's our sample mean. Our S, sample standard deviation, was 0.4888 or so. Our T, the test statistic, is negative 1.936. And the p-value was 0.3058, rounded. Okay, and by the way, you are required to use this calculator for the regular homework and the exams. Okay, just let you know that. Any questions on getting the test statistic and the p-value? Okay, now that we have those, we can state our conclusion. 0.03. I knew there was something wrong. 0.3058. Any questions on that? Okay, we have a 0.01 level significance. Notice that 0.03 is greater than 0.01. So the conclusion is there's statistically insignificant evidence to conclude that the population mean amount of liters that women drink per day is less than 2.7. Any questions on the conclusion here? Okay, here's a template. And again, this isn't something you just copy and paste and don't change anything, but it just helps you. So to give the conclusion, you say there is statistically, and it'll either be insignificant or significant evidence to support the claim that the population, it'll either be mean or proportion, and then it'll be whatever you're talking about. Like in ours was amount of liters that women drink per day is less than 2.7. Any questions on the template? Okay, for the p-value interpretation template is if, and then the null hypothesis is true. So in this case, a null hypothesis was H naught mu equals 2.7. So that would be the population mean amount of water that women drink per day is 2.7. So that's what I mean by the null hypothesis is true. And another sample of whatever. Okay, in this case, there were, I don't know if it says, did it say how many? How many there are, you can count. I'll let you count. Of that many women. Was taken, then there would be it's a p-value, so that'd be a 0.03 or a 3% probability that, and then the results of the new study would be at least as extreme as the results of this study. So in this case, our mean was 2.54. So the way you interpret this part is that the sample mean for the new study would be less than or equal to 2.4 liters per day. Any questions on that? And similarly, the level of significance template is if, so basically with level of significance is exactly the same all up until the word A right here. So in this case, if the population mean amount of water that women drink was equal or is equal to 2.7 liters, and another sample of whatever, however many we took was taken, then there would be A, and our level of significance was 0.01 or a 1% probability. The new study would result in falsely concluding that, and the alternative hypothesis is true in this case, that the population mean amount of water that women drink is less than 2.7 liters per day. Any questions on kind of getting these templates and understanding? Okay, so here's another one. And the great thing about this stuff is it's so easy to just go online and find like whatever's in the news today. So here's another one that was in the news. Do fewer than 50% of all Americans approve of the job Trump has done so far? What do you think? Do you think fewer than 50% approve of Trump, what he's done? Of all Americans? Of all adult Americans, sorry. Because 1-year-olds don't even know. Okay. So the idea we don't know, we'll never know exactly, but what we can do is we can decide if there's statistically significant evidence for it to be true or not. Okay. And by the way, I looked it up, and 45%, which was 453 of the 1,006 that were surveyed, approve of the job Trump has done so far. Okay. And the source is Gallup. So the idea, sure, 45% is less than 50%, but is it enough less than 50% to have statistically significant evidence? What do you think? Okay, let's find out. And the way you find out is you have a H naught, P equals 0.5, that's 50%. H1 is P is less than 0.5, and we need a test statistic and P value. So let's go back to the calculator. What calculator do you think I need? Yeah, number 16, because this is a proportion. Because the survey question is, do you approve of the job Trump has done? And the answer is, yes, I approve, or no, I don't approve. Do you see? Yes or no? And it's a hypothesis test. So our N, if I remember, was 1,006. Yeah, 1,006. Our X was 453, which, by the way, is 0.45 times 1,006 rounded, 453. Our P naught is 0.5, 50%. We want to see a fewer approve, so that's a less than. And then you calculate. And our test statistic now is Z, is 3.1528. And our p-value is 0.000808. Any questions on getting these? I want to remind you, P stands for probability. If you ever answer a question saying the p-value is, say, 1.34, how do you know that can't ever be right? Having 1.34 as the probability. That's the p-value, I mean. Okay, it can't, because you can never have a probability bigger than 1. Okay, so what that really means is you probably didn't look or scroll enough to realize that it was in scientific notation. Okay, and that can happen, by the way. Sometimes you end up getting like 0.00000004, and then the calculator, the computer will write, 4.34 times, and then it'll have an E negative 7 or something. Does that make sense? Any questions on that? The test was negative. I don't know what you mean by that. Do we not add negative? I'm not sure you mean by negative. Here's the calculator. Oh, negative. Sorry, I didn't type the negative. Yep. So not test. The test statistic was negative. Yeah, it was negative 3.1512. Yeah. So I forgot to type that in. Yeah, yeah. And that's because notice it's very far to the left. So that's why you get negative test statistic. Okay. By the way, the p-value is definitely less than 0.05 by a lot. So there is, in fact, we can write strong because it's less than 0.01. There is strong statistically. By the way, if you don't have a level of significance, then you just use the word strong if it's less than 0.01. Strong statistically significant evidence. If it's less than 0.05 but greater than 0.01, you just say there is statistically significant evidence. If it's between 0.05 and 0.1, you say there is weak statistically significant evidence. And if it's greater than 0.1, you say there is statistically insignificant evidence. Just note. So there is strong statistically significant evidence to support the claim that fewer than 50% of all adult Americans approve of the job Trump has done so far. Does that mean that definitely fewer than 50% of all Americans, all adult Americans, approve of the job Trump has done so far? Does that mean that? Because we have strong statistically significant evidence, so we can just say, hey, fewer than 50%. Okay, the answer is no, you can't say for sure. But when you have such a small p-value like this, then yeah, you don't know 100% for sure, but you like it's worth, if you're gonna lose $1,000 because if you're wrong, you actually don't have to worry that much about it because you're right. It's so low. Does that make sense? Any questions on this? Okay. I just want to note something. After you look at the p-value and after you have your conclusion, then you want to say, hey, do you think we need to really have a bigger sample size and maybe redo the study? Maybe that bigger sample size will help. Let me tell you the 3 cases. Okay. And I'm going to do it in a couple ways. The first way I'll do like these example. Here we had a p-value of 0.0008. And we were able to say exactly what we were hoping to say, and that is fewer than 50% of all adult Americans approve of the job Trump has done so far, because that's what our H1 was. So at that point, since that's what you're trying to say, and you were able to say it, no reason for you to do the test again. No reason to increase your sample size. Okay, on the other hand, if you had a p-value of, let's say you have a level of significance of 0.05, and you had a p-value of 0.06, then you would fail to reject, but you're pretty close. Does that make sense? And you go, oh no, I'm really close, but I wasn't able to say that there's statistically significant evidence. So in that case, you say, yeah, I think it's worth it to do another study, but increase the sample size. On the other hand, if your p-value is say 0.54, which is I think what we got last time, then you would say that we're not even close to 0.05, and there's pretty good chance that we were just wrong in the first place. I mean, maybe we were right, but there's a pretty good chance that we were wrong. It's probably not worth our time. Does that make sense? And I like to use the analogy. Imagine you are the soccer coach. Okay. Your team is down 7-6. Okay. So you're losing. And there's 5 seconds left, and your player is about to kick it, right into the goal, possibly. But then the other player knocks, your player down with his elbow. But the referee doesn't say anything. Should you complain? Yeah, in that case, yes, because if you complain and they have a video of it, hey, they'll look at that and say, oh, you know what? We're going to give you an extra chance. It was a foul. Do you see that? Okay. On the other hand, instead of it was 7-6, what if you were ahead 7-6? Same idea, and there was 5 seconds left in the game. Would you complain? Would you yell at the referee? Okay. No, in that case, you don't need to yell at the referee because you're still won the game. Do you see that? So if you win, there's no reason to be a complainer. Let it go. You won. Celebrate. Who cares if you win 8-6 instead of 7-6? Doesn't make a difference. Okay. So if you're winning, if you're able to say, yeah, there's statistically significant evidence, there's no reason to do another sample with a larger sample size. Okay, now let's do another one. Let's suppose, again, now 5 seconds left. And now you're instead of behind 7-6, now you're behind 7-2. And the same thing happens. Do you complain? Yeah, no, you're lost. Okay. You're not going to win the game. You're going to lose. Does that make sense? So you go home, cry a little bit, but there's no reason to like yell at anything at the referee if that's all they did wrong, because that's just 1 point and you still lost the game. Does that make sense? Kind of the same idea for this hypothesis testing. Any questions on that? Okay. Okay. So, do more than 2/3 of all Americans support the US in taking steps to try to reduce climate change? Run a full hypothesis test. Okay. So H naught is P is equal to 0.6667. I'm going to round because 2/3 is about 0.66667. And H1 is P is greater than 0.6667. Do you see that? And there was an article from CBS News. They surveyed 2,230 people, and their sample proportion was 0.7. By the way, is that bigger than 2/3? Is that bigger than 0.6667? It is, but you don't know by looking at it whether the test statistic is, big and is small enough. So we need to go and do the study. So we're going to have N again. N was 2,230. Our X was 0.7 times that. So I'm going to go scientific calculator. I'm going to go to 0.7 times 2,230. And that gives me 1,561. Our P naught was 0.6667, because that was what H naught said. And we want to see if it's greater than that. So it's a right-tailed test because it's the right-hand side. So I click greater than, and I hit calculate. So our test statistic is 3.3359. Our p-value is 0.000425 or so. So what do you think? Is there statistically significant evidence? Yes or no? What do you think? I don't see. I'll jump it in. We have a p-value very small. Remember, small p's are good. P-value is definitely less than any level of significance you'd use. In our class, the smallest one you'd ever use is 0.01. So there's definitely evidence. So we can say that there is statistically significant evidence. In fact, this one's strong because it's less than 0.0001. Statistically significant evidence to conclude the population proportion of all Americans who support the US in taking steps to try to reduce climate change is greater than 0.6667. Yeah, it's super small, and our definition in our class of being super small is less than 0.01. So less than 1%. And that's what most people use. Any questions on this example? Any questions? Okay, I have other examples, but we can only do so many. Oh, I do want to mention, if you go to the LTCC website, Lake Tahoe Community College website, right here, ltcc.edu, and you go to library, and you go find articles, and you go to academic search complete. Uh-oh, there we go. Uh-oh, this isn't supposed to happen. Unable to validate my login credentials, okay? There we go. Maybe the log's down. Sorry. I've never had this happen before. But anyway, if you go there, you can type in the name, you can go search for articles if the site's not down. I'll talk to the librarian tomorrow if it's still not working. But just to note that that's important, and you're going to have to do for the discussion post assignment this week, you're going to have to do a peer-reviewed article, and that's how you find them. Sorry if the site's down. First time that's ever happened to me. Okay, the last thing I want to, well, not the last thing, the next thing I want to talk about is the secret word. And that is population. And I want to remind you, if you're referring to the population mean or proportion, you need to have the word population. If you're referring to the sample mean or proportion, you need to have the word sample. So those words are required. Got it? Okay. So what I want to talk about a little bit is project 2. Okay. So the first thing, what do you think the very first thing, same first thing that you had to do in project 1 is? Yeah, partners. Okay. So the very first thing you have to do is find partners. And you are allowed to use the same partners if you had partners that you're happy to work with again. And they're still in the class and all that. But you don't have to use the same partners. You can use different ones. So just note what I did. If you go to discussions, there's a project 2 discussion forum. No one's posting it yet. But if you want to find a new partner, you hit reply, just like the project 1 discussion forum, but now doing the project 2 discussion forum. Does that make sense? It's nothing different other than it's now project 2. Okay, and I want to let you know, because I graded project 1, honestly, everyone who didn't have a partner didn't get a passing grade, and everyone who did have a partner got a passing grade. It makes all the difference. Okay. And I'm not saying you're guaranteed to get a passing grade if you have a partner, but it's a huge difference. So if you go to the syllabus, the main reason why it's a huge difference, and I said this in the orientation, but I want to remind you again, is there's a 25% penalty for any student that cannot work with another student. Okay. And again, 3 is easier than 2, but 2 is allowed. Okay. So you don't lose points if there's just 2 of you. But if there's only 2 of you and your partner drops, you're screwed. So that's another reason why 3 is better, because it gives you that backup. Okay. So very, very important to have partners for your project. Okay. Any questions on that? All right. I'm not going to go into the details of Project 2 because we'll do that next week. I do want to just give you kind of a couple of heads up. First thing, you're not ready yet to do the project because next week is when we're going to be talking about it and doing the statistics that you need to know. But I will tell you that the main point of the project, there'll be 2 main points. First is confidence interval. Second is a hypothesis test. So notice that although it's really chapter 10, but chapter 8, we talked about confidence intervals. That was last week. And then today and this week, we are talking about hypothesis testing. Next week, we're going to be talking about comparison studies. And your project will be a comparison study, but we're not ready to get into the details of that yet. So I do want to let you know that. I also want to let you know you do have to use the spreadsheet that I created, and you have to copy and paste the important pieces of it. And I'll show you the important pieces for the next project next week. We're not quite ready yet, but a lot of you didn't do that for project 1 and you lost points. Okay, you don't do it. I'm pleading to do it. Okay. And if you don't know how to copy and paste, I'll help you. Just log into student hours. I'll show you how to do it. It's not that hard. You just either copy and paste, or if that doesn't work, you can do screenshot and then put the picture of the screenshot into your project. Okay, which is also pretty easy. I am better with PCs and Macs, but and Chromebooks and Macs, but it's not that hard. If I had to help you with the Mac, I just ask AI, it'll tell you how to do it. Okay. And those are the things you should use AI. What you should not use AI for is writing your project. Don't even think about that. And I can tell, by the way, and I grade much harsher if you're using AI. Okay, I know. Okay, I've done AI coding actually, so I know what it looks like. So don't use AI to write your project. Any questions, just general questions about the project? Okay, and kind of similar timeline is that this week you should make sure you have your partners set up. Next week, you should decide on what your project is going to be. Okay, who your client is, what you're going to be getting data from, and your strategies, and what your H0 and H1 are in this case, because we talked about that now. And then the week after that, you collecting data will be easy on this project, just let you know that. If not, then you wasted your time. And then you do the full analysis of it. And then I recommend like a week before the project, send me your draft. I'll look at it and give you suggestions. And that makes a big difference, by the way. I noticed those who sent their rough draft and gave me suggestions did a lot better on the project than those who didn't, on average. Okay. So any questions at all about the project? If there aren't questions, it's 7:30, and that's kind of my goal is around 7:30. If it's 7:35 or 7:25, I don't mind too much, but my goal is around 7:30 to finish. So, and I'm always happy to answer questions after we stop the video recording. But if there's any questions, you can ask now too. So I think I'm going to stop the recording. And thanks for watching this. And make sure you do the secret word quiz by Sunday. That's really important. Otherwise, and by the way, this whole 5-page note thing, That's if you don't do the secret word, but I still recommend writing notes when you're watching the webinar. One thing, it keeps you focused, so you don't get as distracted if you're writing notes, because then you're actually listening and writing. So writing notes is actually real helpful for learning. Just let you know that. It also helps you remember because you're physically doing something that is involving what the lecture is about. So I do recommend writing notes. So I think I'm going to stop recording.